Let's start with a simple question. When humans look at a picture of a cat, we can usually recognize it instantly. But a computer does not see a cute animal. It does not see fur, ears, or whiskers. To a computer, this image is just a big table of numbers. So the real question is, how can a machine look at these numbers and decide, yes, this is a cat? That is exactly what a CNN or convolutional neural network is designed to do. You can think of CNN as an image detective. The cat is already hidden inside the image. CNN's job is to find the clues. In a computer, an image is not stored as a picture in the human sense. It is stored as a pixel matrix. Each tiny square in the image has a number. That number represents brightness or color information. For a grayscale image, each pixel may be one number. For a color image, there are usually 3 channels: red, green, and blue. So humans see a cat, but the machine sees a stack of number grids. CNN starts from these numbers and tries to discover useful patterns. You may ask, why not just feed the whole image into a normal neural network? Technically, we can do that, but it is not a smart idea. Images can be huge. If every pixel connects to every neuron, the number of parameters becomes enormous. Even worse, images have spatial structure. A cat's ears, eyes, nose, and whiskers are all local patterns. They are built from small regions. If we flatten the whole image too early, the model may lose these local relationships. So CNN uses a smarter strategy. Do not look at the whole image at once. First, look at small local areas. Now, the convolution kernel appears. You can think of a convolution kernel as a tiny detective with a small window. This window is usually a small matrix, such as 3 by 3 or 5 by 5. It does not try to understand the whole image at once. Instead, it looks at a small local region and asks, is there an edge here? Is there a texture here? Is there a corner or a useful pattern? In simple words, the kernel is CNN's local scout. It looks at small areas and searches for visual clues. The convolution kernel does not stay in one place. It slides across the image step by step. Imagine a detective walking through a crime scene, checking one small area at a time. At each position, the kernel performs a small calculation with the pixels under its window. Then it writes down the result. When it finishes scanning the whole image, we get a map of responses. Where the pattern is strong, the response is high. Where the pattern is weak, the response is low. So convolution means slide a small window across the image, calculate local responses, and record useful features. After convolution, we get a new image-like result called a feature map. A feature map is not the original cat image. It is more like a clue map. It tells us where certain patterns appear. For example, one feature map may highlight edges. Another may highlight textures. Another may highlight bright spots or shapes. You can imagine each convolution kernel as a different detective. One detective is good at finding edges. Another is good at finding textures. Different kernels produce different feature maps. Together, they help CNN understand the image step by step. After we get a feature map, we often apply an activation function. One of the most common activation functions is ReLU. ReLU is very simple. You can think of it as a security guard at the gate. Negative values are not allowed in. They become 0. Positive values can pass through. So ReLU keeps useful positive signals and removes negative responses. This does 2 important things. First, it cleans up weak or unhelpful signals. Second, it helps the neural network learn more complex, nonlinear patterns. A simple way to remember ReLU is negative values go to 0. Positive values stay. Next comes pooling. Pooling is like compressing information while keeping the most important parts. For example, in max pooling, we look at a small region and keep only the largest value. It is like packing for a trip. You cannot bring everything, so you keep the most important items. Pooling makes the feature map smaller. That means less computation and less memory. It also makes the model more stable. If the cat moves a little bit in the image, the output should not change too much. So pooling does 3 things. It reduces size, it keeps strong signals, and it makes computation cheaper. A CNN usually does not use only one convolution layer. It stacks many layers. The early layers usually learn simple features, such as edges, lines, and color changes. The middle layers start to combine these simple features into textures and small shapes. The deeper layers may recognize eyes, ears, noses, and even the outline of a cat face. This is like an investigation team. The junior scouts find basic clues. The analysts combine the clues. The commander understands the full target. The deeper the network goes, the more abstract the features become. Many CNNs repeat the same basic pattern: convolution, ReLU, and pooling. Convolution finds features. ReLU filters signals. Pooling compresses information. Together, they form one round of feature extraction. After several rounds, the model no longer sees raw pixels, it sees higher-level features. You can think of this like leveling up in a game. Level 1, find edges. Level 2, find textures. Level 3, find parts. Level 4, understand the object. With each round, CNN gets closer to the final answer. After multiple rounds of convolution and pooling, we have many feature maps. But for final classification, the model usually needs a one-dimensional vector. This is where flatten comes in. Flatten takes the two-dimensional feature maps and stretches them into one long list of numbers. It is like putting all pieces of evidence on a table. Then the fully connected layer comes in. You can think of it as a panel of experts. It looks at all the evidence and decides, does this image look more like a cat, or a dog, or a car? So flatten organizes the evidence. The fully connected layer makes the final judgment. At the end, the model outputs a probability for each class. For example, cat, 0.92, dog, 0.06, car, 0.02. The class with the highest probability becomes the final prediction. In this case, cat has the highest score. So the model says, this is a cat. Now let's connect the whole process. Input image. Convolution finds local features. ReLU filters signals. Pooling compresses information. Multiple layers combine simple features into complex ones. Flatten organizes the evidence. Fully connected layers make the final classification. In one sentence, CNN is like an image detective system. It first looks for local clues, then combines them layer by layer, and finally votes for the most likely answer.